Thank you. So my name is Moritz, I'm from Magazzino, and we're presenting today joint work with Google on how we can use different robots for mapping an environment, for integrating the information from these robots coming in order to have a consistent view of how the world is actually looking like. So why do we want to do that? So with Magazzino, we are building mobile pick-and-place robots that should be shown in this video here. You're going to see the video on our booth as well. So the important thing is we have mobile robots. They navigate through the warehouses autonomously. They can pick items, they can stow items, and basically do the same job that humans are doing. While they're driving around, they're also interacting with humans who are operating in the same warehouse. So the humans also pick items, put items, change the environment by this. And in addition to safety requirements, the robots also have to cope with all the uncertainty that the humans introduce into this world. And what's very important, of course, we want to sell these robots to customers. They are already in live operation. So for the robots to pay for the customers, they have to be, on the one hand, fast, and on the other hand, they have to be reliable. And in this talk, we're talking about how we can help the robots to become both by having better information about the environment. So the video didn't really play, but let's have a look at these animations. So this is like a top-down view of the warehouse. So you're seeing some rows of shelves. You see some humans, these long, elongated squares are like pick carts. So you can imagine they're like shelves on wheels that they are pulling around for putting the items in. And in between you have some robots that are driving, that are also picking. And of course, you have lots of objects that are lying there. In our cases, it's often like shoe boxes or other kinds of things. And in the morning, the shelves are normally pretty full. Over the course of the day, the humans and the robots pick items, everything that you ordered online, all these shoes. And they continue picking, and in the afternoon, the warehouse actually looks pretty different. And it looks different at the high level, at the semantic level of which objects are located where, but also at the low level of, if you look at it at the map, at the height of the laser scan, then you just see different things, and the outline of the environment has just changed a lot. And if we want to, remember, we want to be fast and reliable, we need to ensure that the robots know where they are. So they need good localization in this area, but they also need to know where the objects are. So imagine the red robot wants to pick the item that is there, this red box. The warehouse management system only tells it it's somewhere in this area here, so it's somewhere on this shelf. But in order to really pick it and already drive to the right location, in order not to have to search, the robot better knows where exactly it is so that it can plan its path. And the problem is, of course, the more humans are there, the more robots are there, the faster the environment changes. And in order to have good data, have a good belief about the environment, we need to have frequent updates. And we increase the sampling rate by integrating data from different robots, feed them into a common belief state, and by that, we want to have very good information. And that's also where we collaborated with Google on seeing how we can actually leverage this data and how we could use or extend cartographer, a localization and mapping system in order to help with that. So Andre from Google will explain more about the algorithms behind that.
Hi. So I guess it's become quite clear that we need dynamic mapping, we need cloud-based mapping. And we at Google, we developed the open source software Cartographer. Cartographer is a software for simultaneous localization and mapping, SLAM. And it offers 2D and 3D algorithms. So you can use 2D and 3D laser scanners, LiDARs, and it's around on GitHub as an open source package. We recently released the ROS package version 1.0, and it's not only been used by mobile robot companies, but also by researchers and internally with Street View. So what is Cartographer about, and how does it help with cloud-based mapping? So I will briefly explain the algorithm, and then we will later see how Magazzino uses it in practice. So starting from the lower row, we have LiDAR sensors, laser scanners, we have inertial measurement units, we have wheel encoders, and these sensor data feeds into the SLAM algorithm. In Cartographer, we do scan-to submap matching. So what does this exactly mean? So the SLAM algorithm receives a LiDAR scan that pretty much looks like a like a small point cloud that shows the reflections of the laser rays. And we match this scan against a short time accumulation probability grid, which we call a submap. So the submap is a probability grid of occupancies, and we match it against the submap. And this gives us the estimated pose by scan matching, and we insert this scan at this place into the submap. So we do localization and mapping. Of course, this is SLAM without loop closure. Loop closure is important because so far every scan insertion will have a tiny error, and this drift accumulates over time, so we need to cancel out this drift. How do we do this? We feed the limited time submaps into a pose graph, which we can then optimize and find additional loop closures. So before loop closure, when you map a large area, like on the left side, this a sensor walking around a very large museum, working in a large circle, and this oval room in the museum you can see double because it was recorded in the beginning and in the end, so it's really double recording. And with loop closure, we run scan matching from the current scan to old submaps. And here we can find a match, and that match enters into the pose graph as a constraint. And then the pose graph optimizer can move pieces together and optimize the pose graph. So this is really important to provide a good quality map. So this is one important piece of the algorithm. The second important thing, of course, is how do we do localization? We really do global localization. So when we talk of a map in Cartographer, it's not a bitmap, but it's really like a frozen pose graph with all the information attached. So when a robot moves around and needs to localize, what it does, it matches the currents. It tries to match the current laser scan against the existing pose graph, against the submaps in the existing pose graph. And when it finds a scan match to the existing map, that's really, you have the pose graph of the current motion, and the map is the frozen pose graph, and then you combine, you have a connection between these graphs, and that helps you that the current pose is really localized in the coordinate frame of the frozen map. So that's global coordinates then. So this is the localization procedure of Cartographer. What else do we need? Of course, for cloud-based mapping in these dynamic environments, we need to have collaborative mapping. So the robots usually, they run SLAM in a finite history configuration, so that means they keep only submaps over a certain time scale. And of course, they provide very low latency pose, so that can be used for robot control. And they do global localization, which in our case is really loop closure to a frozen map. So that's what each robot does. And then each robot upstreams data to the cloud or to a central cloud-based mapping instance. It can also be on an edge server. It upstreams the submaps to the pose graph optimization that runs in the central instance. And the pose graph optimizer can even find loop closures across the different trajectories of the robot. So it really comes out with an optimized map of the entire area. The only missing piece still is that we are only recording data, but the map grows and grows, and the pose graph has more and more layers. So we also need means to erase old data, and that's the lifelong trimmer, that's lifelong mapping. So we came up with a very, very simple approach to lifelong mapping so far. It's the easiest such approach you can imagine. It's just we have the submaps in the pose graph, and we look how old they are and which area they cover. And if a submap is old enough and has only a small unique area that gets lost, if I erase that submap, we just remove it from the pose graph. So that's what we call the lifelong trimmer. That's a very easy solution for this problem. Yeah, and essentially these are all the building blocks of the Cartographer algorithm. that are necessary for this task. And now Michael will present how this is plugged together in practice.
Yeah, my name is Michael. I'm working at Magazino on SLAM. And yeah, I'm going to come back to the initial problem that Moritz was explaining, which is the dynamic warehouse, in which our robots are operating, picking objects, and have to cope with all the changes that are happening in the environment. So first I'm going to start with the conventional approach that probably most people are more or less familiar who are working with localization. So we used cartographers since about a year, and so far our approach was not to have a cloud-based instance for mapping, but to have the mapping separated from the real-time operation of the robots. So what does this mean? We have our robots that are running the real-time localization with a finite history. So you can really imagine this like sliding window of submaps. So you don't keep all data on the robots, of course, because you have limited resources. And rather, you do the mapping as a separate process. So every time that the environment changes, so this can be on a weekly basis or a monthly basis, depending on the environment, we have to remap and load this static map onto the robots, which they then use to find loop closure constraints. So here's a GIF of this process. You can see a single robot, going on a dedicated mapping path through a warehouse environment and capturing the current state of the environment. So we invested quite some time in this conventional approach to make it robust and increase the quality of the maps. We also have a automatic waypoint generator for the warehouse to remap. So the whole process is not manual, but you can send a robot on this path. And that's what we have been doing the past month, basically. So it works fine from a mapping point of view, but there are some problems with it. So as you can see, the robot is driving basically through an empty warehouse, which is problematic if we think about that we want to have multiple robots working in a warehouse environment. And those robots shouldn't be blocked by mapping. So first of all, we need a mapping robot that is going on this path, but we also need to remove all the other robots so the mapping doesn't take forever and the mapping robot is not blocked. So the whole idea of this cloud-based mapping project was why do we need to send a robot on this complicated path if we have this by all the time, which is basically all robots operating in different areas of the warehouse, seeing the current state, and then using this state that the robots see to assemble an updated map. So how does the component, from component point of view, how does the migration look like from this conventional approach to the cloud-based approach? So on the robot, we didn't want to change much. So because we have limited resources, we still want to use the same basic approach for localization. We have a frozen static map and try to localize within in more or less real time. And also we didn't want to change any APIs for the rest of the robot. What's now new is an uplink on every robot that is communicating via the gRPC framework with a cloud instance, which is optimized for mapping. So it's basically a separation of concerns. The robots do their task, they manipulate objects, do only real-time localization, but we do the mapping on a more powerful cloud instance that we can also scale to our requirements. So the robots are sending their observations, which are submaps and sensor data, to the cloud instance. And we regularly update the map on the robots by downstreaming it from this cloud instance to the robot. And because we can basically scale theoretically to unlimited compute power in the cloud, we can scale this to multiple robots operating in big warehouses. So, yeah. We piloted this approach. First of all, we started in our lab. So this what you can see here is our mini warehouse at Magazzino. It's basically a small warehouse. We have the same type of boxes, same type of shelves. Of course, a small environment, but we can use it for testing and here to illustrate our approach. So what you can see here is basically we have an obstacle that is this big cart filled with boxes, and we intentionally placed it there to illustrate the bigger picture that we want to achieve in the next month with this whole project. So the idea is that the robot that you just saw drives by this obstacle, and by driving by, it can capture this obstacle with its local slam approach. So you can see the obstacle appeared in the right location, which is here on the left in the video. And in the future, we want to use this updated belief state, you can say, of the environment to share it with the other robots also in real time. So imagine another robot that is also driving to the same warehouse that wants to get to a position near the obstacle and is now getting the information from the other robot that has mapped the obstacle and is now able to replan according to the updated map. So initially the shortest path was where the obstacle was located, but since we now have updated the environment representation, we can use this to replan and go another path which is actually longer, but in this case more optimal. Yeah, so this is visualized here in this video. Yes, the other robot is basically going the other path. So what you see here is, of course, a toy environment. This is not a real warehouse, but we are illustrating what we want to achieve with it here. So that's why we're showing it. We did not only test in our own lab, but we also deployed it to a real warehouse. So the same warehouse that I showed you before in the mapping video, we used for pilot test of the cloud cartographer. And we used 3 robots and a cloud instance. And what you see here in this animation is a comparison of the state of the map that the robots used for real-time localization versus the state of the map server at the end of the day. So the blobs that you're seeing in the 2D maps are mostly boxes that are located in shelves and that have been moved. And with the cloud-based mapping approach, we were able to capture all these movements, all this dynamic environment changes from robots operating in a normal setting, just doing their tasks and picking objects. And also we were able to tune it that the quality was of the map itself is staying the same, so you don't see any larger geometric distortions from this live cloud-based mapping. So that was our presentation on cloud-based mapping. If you have any questions, feel free to ask us. An important thing to note here is maybe also that we're not developing this in the secret. So you can find the source code of the core components on GitHub. And feel free to come by our booths of Magazzino and Google. And we're hiring. So.
Thank you very much. Looks like we got a question.
Yes, my question is, I've also experimented with cartographer a little bit, and I was wondering if you were able to get it to map accurately across different maps, but only using wheel encoder and 2D LiDAR without an IMU.
So we currently use an IMU. We use wheel encoders, IMU, and laser data because that's all we can use, and why discard it in this case? But we were also able to use it without an IMU. So I don't know what if you had any problems with tuning without an IMU. Maybe you can elaborate here. So
Yeah, I mean that was the.
So we were able to do this. So
Okay.
but there are many parameters you can tune. You can use also a front end that is based on the loop closure search algorithm, so the real-time correlative scan matcher, which is actually recommended if you don't have reliable input from an IMU. So you can try that. And, yeah.
Okay, thank you.
Looks like we got a lot of interesting questions. We got time for one more because I got to get you moving on to the next things.
So first of all, very cool stuff. It's kind of a lot of the things that we've been thinking about as well. So my question is, how do you deal with stale information? So for example, let's say you have a robot that goes down a really long aisle, sees a forklift kind of parked there, puts it in the map, gives that to all the robots, and now no robot is going to plan down that path. But eventually that thing's going to go away. So do you have any kind of decay?
So, I mean, the idea would, if we have some semantic information from other sources, like for example a warehouse management system. So we have some information that we get from the customer, for example, where objects are located roughly in the warehouses, whether they have been manipulated or not. Of course, in case of a forklift, you have to make sure that this also gets streamed to your environment representation. But I think if you have some semantic annotation that this object is a volatile object that is moving, you could then mark this area as an area with a high probability of being dynamic. And also, I know what you mean when you have objects, also other robots standing in hallways, you would eventually map them too. So I would then incorporate all information we can gather from multi-robot coordination, warehouse management system to define a prior that this is probably being resolved after some time. Yeah.
Cool, thank you.
Thank you very much.